Quicksilver solutions of a q-discrete Painlevé.
Thank you, Rod. Is this on? Okay. Thank you very much to the organizers of this workshop. It's lovely to be back. I think I've been to something like 4 or 5 Newton Institute programs starting in 1995. And it's always been a wonderful time as far as I could judge, mathematically and personally. And at the DIS meeting in 2009, I'm sorry, I'm severely jet-lagged and I can't remember any time information right now, was where I met Dijkstermaat, and that was a fantastic start to a collaboration which was unfortunately cut short by his untimely death the year after. So it's wonderful to be able to speak about some of the work that was inspired by the start of that collaboration here. So as I said, I'm quite jet-lagged, and hello to fellow sufferers in the audience. So I hope you will allow me to indulge in my dreamlike state in a metaphor to begin the talk. So to me, integrable systems are like stars in the sky. We are all, I think, very practiced at inventing and refining new telescopes to search for new stars and to classify new galaxies. And we are very, very good at it. But I would like to respectfully suggest that there is a part of the work that needs equally intensive amounts of effort, and that's to study the properties of their transcendental solutions. And this is the kernel of the work that I'd like to present to you today. So, my telescope is a geometric one, which was first invented by Okamoto. He showed in 1979 that the Painlevé equations can be thought of, this is the classical continuous Painlevé equations, can be thought of as dynamical systems on a rational surface that's obtained by blowing up 9 points on complex projective space of dimension 2, or 8 points if you're considering that space as the cross product, the direct product, P1 cross P1. Since then, of course, Sakai did a tremendous amount of work to extend that point of view and discovered new discrete Painlevé equations and gave us a totally universal point of view about the Painlevé equations in general, discrete and continuous, together, combined. But what do we know about their transcendental solutions? We know quite a bit for the class of discrete equations called the D Painlevé equations, because they mostly arise as contiguity relations of the continuous ones. We know a lot about their special solutions in terms of rational algebraic or classical hypergeometric type functions in work that's been led by Nomi, Kajiwara, Yamada, and many others. But for the Q Painlevé and the elliptic Painlevé equations, we know almost nothing about their transcendental solutions. That is, the ones that can't be expressed in terms of earlier known functions. So, to set the scene a little bit, let me explain how to understand that geometric point of view just very briefly. This is my very poor attempt at trying to draw a picture in P1 cross P1. If you look at the equation at the top of the slide, this is known as Q Painlevé 3. If you think about the factor gamma and the zeros, mu and u, as functions of an independent variable, let's call it n. I haven't written down all the details here, but if you think about them as multiplicative functions of n, so mu and u, functions that look like this. I've called it lambda rather than q, but typically q is the parameter used in that context. Then consider the equation on in P1 cross P1, then and writing it as a system of two variables, I've called it u and v, then it's very easy to show, and I'm happy to go into details later if you'd like me to, that there are points, special points in this space, in this projective space, through which all the iterates of the solutions continue. In other words, another way to think about it is if mu and u were constants, so that what you have here is a QRT map, then where x is equal to, where you have a 0 of the numerator and a 0 of the denominator, and that, for example, happens when x lower bar is 0 and say x is equal to mu over gamma, then you have a base point of this equation. A base point is a point through which all the pencil of the invariant curves goes through in this space. And whether you're looking in the original coordinates in finite space, in the finite domain, or where one of the coordinates u or v becomes infinite, so that you're looking in different patches, you find 8 different points of this system, which are the base points of the equation. And in this space, if you now come back to mu and u being not constants anymore, but functions of n like these, then what you see is a picture like this, but each time you increase n or decrease it, you get a slightly different picture. You have a non-steady flow. Each of the points will, some of the points will move with n, and so what you get is a foliation of slices of this kind that are strung together by n. So that's the geometric picture behind the equation, and this space can be thought of as A51, that is the affine extended the algebra of called A5. If you're thinking about, for example, the intersection diagram of the exceptional lines, what you get is the corresponding Dynkin diagram of that algebra. So that's a very quick picture of what happens with the solutions of these equations. There's some tremendous work going on in Japan using this point of view, and what I wanted to do was to try and start understanding how we can use the geometric picture to understand the solutions of these equations. So in particular, I'm going to focus on QP1. QP1 is a degenerate limit of QP3. It was probably first written down, please correct me if I'm wrong at any point about the history. It was probably written down in a paper by Ramani and Grammatikos first in 1996 in a paper that's called Coalescence and Degeneracies of the Painlevé equations. And this is a limiting case where gamma in the previous equation goes to 0, and certain other things happen in the limiting, in the values of the parameters, so that certain things cancel, and you can rewrite that equation in the following form, where instead of, I now change variables to g being the dependent variable and x being the independent variable. So this is a simpler equation just as an example to look at, but also I chose it because it becomes my favorite Painlevé equation in the continuum limit, which is the first Painlevé equation, and that's this differential equation at the bottom. Y as a function of t satisfies this equation. And this is a very important equation, not just because it's my favorite equation, but because it turns out to give universal solutions, solutions that are universal models in many different contexts. For example, in the work of de Brovin, Grava, and Klein, looking at gradient catastrophes of PDEs. Okay, so I'm going to focus on this equation, but another reason for focusing on this equation is that the equation, let me first scale it a little bit so that you can see how to simplify the parameters in the space, in the equation. So remember that there's an alpha and a beta here, but I know that I can scale them away, so that's what I'm about to do. I'm assuming neither of them are 0. Sorry?
Alpha depends on n here.
That's right. I'm sorry, I didn't write that down. It's different in different papers, but they are all the same equation. Alpha is q to the n, or q tilde to the n, and beta is the square root of that to the n. Okay, so I can rescale it, and when I rescale it in this way, what I get is this simpler looking equation where the alpha and the beta have been scaled away now, and C is my new name for the independent variable. I've taken various fractional powers just to make sure everything works out at the end of the day. Now this is a rescaled version of QP1, and its initial value space, as it was for the previous form of the equation, is this object A71. It's the affine extended Lie algebra A7. So what happens with this equation? Well, let me show you that if you take this form of the equation, then the base points become much simpler or in some ways, but very degenerate in other ways. So once again, I'm thinking about base points in the following way. Suppose I take the symmetric form of the equation, and I write W is U and W lower bar is V, or I always use different variables, and I'm always confusing myself. So let me think for a moment which way around I wanted to do this. So you can see that U is going to be, I have, so if I rewrote the equation, in this way, then what I have is over U squared V, and V bar is U. And just for ease of writing later, I may rewrite this as T in a moment. But you can see, for example, that when the numerator vanishes, that's when U is equal to T, and the denominator vanishes. Well, if U is equal to T, this term can't vanish. So the only other place where this vanishes is at V. V is equal to 0. So we get a base point at U is equal to T and V is equal to 0. And because it's a symmetric equation, invertible equation, I can also do the same thing going backwards. And so what I see is that in U and V space, I have a base point here at T and 0, but also the backwards one will give me a T shifted backwards over here. And then if I look at this equation again, but in new coordinates out near infinity, so to look at infinity, so this was at U and V coordinates, but I can also look at 1 over U and V coordinates, or I can look at 1 over V and U coordinates, or I can look at both of them possibly becoming infinite. So I should use 1 over U and 1 over V as coordinates. And then you get 2 more base points that you see, which are at the origins of those 2 coordinate charts. And those are obtained by merger of the ones that, the 8 that we saw in the previous diagram I showed you for QP3. So we have base points down here, remember? And I'm going to look at a limiting case of this equation in a moment, where C goes to infinity, which means that T becomes 0. So these 2 base points will start to merge. Okay, so I wanted to look at solutions, and what about the solutions? Well, a few years ago, Nishioka proved that this equation, QP1, or actually a different form of it, but equivalent to it, has no solution that's expressible in terms of any solution of a first-order difference equation, and thereby implying that there are no solutions that are expressible in terms of functions that solve linear equations. And so it has no rational solutions, no hypergeometric type solutions, no solutions other than new transcendental functions that haven't been described yet. So if we want to understand the solution space, we have to try and capture properties of these things that haven't been described yet before. So that's what I wanted to do. And so before I get to that asymptotic limit, let me just show you that, remember the equations over there. In the limit, c goes to infinity, and by convention, we take q is either bigger than 1 or less than 1 in modulus. If you want to look at where it's equal to 1, things become quite hairy, as for any q difference equation. I'm going to look at away from, a little bit away from the origin. The limiting equation is obviously that one at the top. I don't know if I have a pointer here, but anyway, yes, I do. So this is the limiting equation, and that's another very degenerate QRT type map with an invariant that you can work out. This is the invariant, where I've now used x and y instead of u and v like I did over there. So this invariant curve has special cases. You can, for example, check where it might have multiple points. That is, where if I multiply this out and look at the polynomial equation, where that polynomial has double zeros, for example. And you can find special values of h for which you have double points on the curve. It's like looking at the phase plane diagram of the plane pendulum. There are always generic curves in the phase plane. Sometimes they're closed contours, sometimes they're just extended contours, and then there are special cases that pinch together into homoclinic and heteroclinic type values, points. So there are those kinds of points you can find here. Okay, so let me compare it for a moment with the continuous Painlevé 1 equation, about which we know quite a bit now, seeing that the study of its solution started with Boutroux in 1913, exactly 100 years ago. So what do we know? We know that the continuous Painlevé 1 also has no rational or classical solutions. There are various things you can do. There's an incredible amount of detail we could go into, but for the moment, let me just point out that there are two types of solutions that you can separate asymptotically as you go out towards infinity. And this is a numerical picture in the complex independent variable plane, which came from a paper by Bent Fornberg et al. The numerical study of the Painlevé equations has become better and better in recent years, and you can find quite very accurate pictures now, numerical pictures. This is a picture of a solution which has, the generic solution has an infinite number of poles, and what you're seeing are the peaks of those poles. But there are special values of the initial value, let's say the initial value is at the origin, for which you start seeing the poles move away to infinity as you approach those special cases. And so you have solutions which are called truncae by Boutroux. These truncae solutions are asymptotic to a power series in a large sector. Once these poles have moved away to infinity, you see just very nice algebraic expansion behavior. And so that's where I got started to look for asymptotic series that are algebraic series of solutions for QP1. So just to give you slightly more information, I know I'm not supposed to talk about continuous equations here, but it does give me a framework to launch off to look at the discrete cases. So let me just point out that these solutions with the algebraic series, they have this as an algebraic series. This is a formal expansion because it diverges. The coefficients here grow like the factorial squared. So it's very, very fast divergence. But nevertheless, there's a unique true solution, a real true solution that's free of poles on the positive real axis. This is the real tree-truncated solution, as it's called. And my question at the starting point was whether QP1 has such solutions. So I started by looking for expansions. And remember that the equation's over there on the board. And I'm now going to look for cases that I can expand. And so I started with solutions that look almost stationary, that are almost stationary in the limit. That is, the iterate is approximately the same size as the function that you're iterating. And so in that case, you can see that if I multiply out the denominator, what I get on the left is w to the fourth, and that has to go like w, and that's this equation here. And so I have 4 solutions. Either w cubed is 1 or w vanishes to leading order. And I'm going to concentrate on that last case here. And the omega here is a cube root of unity, but I can, without lots of generality, I can just concentrate on where omega is equal to 1 because it's rotationally symmetric, and I can capture the others by rotation. So if I've got that kind of starting point, how can I go ahead? Well, it turns out that those starting points give me a very explicit way of generating series. I just have to start using a recursion on the equation with that starting point. And the first case, where w was approximately 1, has this series behavior in powers of t. And I've written that wrongly. I'm sorry. That t should have been a xc. That xc is going to infinity, so that's that fraction is going to 0. You can work out the recursion relation. And I should point out that Oyama-san also did this many years ago. I'm not quite sure what year his first paper on this was. He also studied formal series expansions, but he started with the iterate being a particular value, and for whatever reason, he didn't get the recursion relations or the subsequent results about the true solutions that I'm going to show you now. So what about the other case? So that was one case. And the other case, the one that I'm going to concentrate on here, where w is going to 0, then the solution is a series like this, starting with the 1 of xc term. And once again, you can derive the recursion relation. It turns out that these are reflecting the scaling that I did. Remember, I had cube roots in the scaling. That's reflected in the result that only every third coefficient is non-zero. So to put you out of suspense, let me tell you what my results are. The vanishing solution approaches 2 base points. Remember that I have these base points over here. And so if I'm looking at where w is vanishing, that means u and v are vanishing. So I'm in the neighborhood of the origin here and very close to, and I'm actually approaching the coalescing base points. And that makes this solution extraordinarily complicated. But I can expand it explicitly. But reflecting that complication is the fact that that series expansion is formal because it's divergent. It's an asymptotic series, but it's not an analytic expansion. So what can we do with it? Well, fortunately, it turns out that you can prove that there is a true solution with this asymptotic behavior, and it is unstable in the initial value space, in the same way that the truncated and the tree-truncated solutions turned out to be for the Painlevé 1 equation. But there are some differences, and I'll come back to that difference. So how did I prove these? I think I'm running out of time, so I won't give you all the details. The divergence is very interesting. You can show that the coefficients grow, the non-zero coefficients grow in this way. Remember, I've taken q to be bigger than 1 in modulus. It's growing like a quadratic in the exponent. And that's typical of divergent q series. The fact that every third one is non-zero is reflected here. Nevertheless, you can apply a theorem called the Borel-Rit theorem to show that there is an analytic function which has this asymptotic series, but you don't know whether it's a solution of the equation. So the next step is to show that what you are doing is actually capturing a true solution. And for that, you need to look at the linearization, which is very nice. The behaviors of the linear equation can be found. These are like the exponential solutions to a linear ODE. And then I have to convert the equation after linearizing it. So this simple looking equation I can transform to a summation equation. For an ODE, you'd convert to an integral equation. Here you have a summation equation. With those linear solutions as coefficients, you can prove that this thing is well controlled, and you can apply the contraction mapping theorem to this to find a fixed point, and so you get a true solution. All right, so what are the distinctive properties of this solution? They are, I think, as far as I can tell, the first known true solutions of any q-Painlevé equation. I believe they also exist for other discrete Painlevé equations, not just q ones. But they don't correspond to a double or multiple point on the invariant of the corresponding autonomous equation. So they're not like trunqué solutions, which are double points. And they are not providing separatrix type solutions in phase space. So I needed to find a new name to distinguish them, and I decided to give them this name, Quicksilver, and thank you, Claude, Vive l'argent, Vive argent, or Quacksilver, or Suigin in Japanese, because they are unstable and hard to control and hard to pick up in the phase space. Thank you.
Any questions? So do you believe these sorts of solutions that you'll always find solutions of this type for all of the q-Painlevé equations?
And also for the elliptic Painlevé. But there's a lot more that needs to be discovered. Yes.
Any relation, a direct relation to trunqué solution?
By direct, do you mean do they go to the trunqué in the continuum limit? It's very difficult to do the continuum limit for a particular solution. So you could ask the same question for example, for other types of solutions, special solutions. Because the base points are making things very complicated, I don't know the answer to that. Not yet.
So do you expect a similar solution to the additive case?
Yes.
So this is not a Q specific?
No, it's not. But I wanted to do the Q case because it was unknown.
No further questions. Let's thank Nalini for a